Today we are going to discuss about the eigenvalues and the eigenvectors. We are going to learn the definition, the ideas of what it means by eigenvalues and eigenvectors, how to find them, and how to apply them to compute iterated matrix vector multiplications. First, we have the definition. Let's consider an n by n matrix A. A non-zero vector x is said to be an eigenvector associated to the eigenvalue lambda if A times x equals to lambda x. The lambda, the scalar here, is called the eigenvalue. And the vector x associated to this lambda is called the eigenvector. Now, the fact is that if you multiply a matrix with a vector, that's like you apply a linear transformation on the vector. Now, the linear transformation on a vector will usually give the vector a little bit rotation and a little bit scalar multiplication. However, there are some special vectors whose matrix multiplication does not rotate the vector. It only gives the vector a scale. Now, each of the eigenvalue, the eigenvector associated to the eigenvalue, is not unique. For example, if x satisfies this equation, then A times a scale of x, because you can see that it's going to be equals to c times ax, and it's going to be c times lambda x because of this, right? And so this is like you have A times the scale of x equals to lambda times the scale of x. So if you have a vector x that satisfies this equation, then any scale of x would satisfy the same equation with the same lambda eigenvalue. Furthermore, if you have two vectors x, x1 and x2, that satisfy the same equation with the same lambda, then the summation of the two will satisfy the same equation. That means all of the solution associated to the lambda eigenvalue is actually a vector space. And this vector space has its name. It is called the lambda eigenspace of A. Theorem 5.1. Let A be an n by n matrix. Then lambda is an eigenvalue of A if and only if the determinant of A minus lambda I equals to 0. So this is a very nice theorem because it allows us to compute the eigenvalue for A. Of course, after we know the eigenvalues, we can just substitute the eigenvalues into this equation, and then we can solve for the x. In this equation, the left-hand side, if you really compute the determinant of A minus lambda I, the left-hand side is going to give you a polynomial, and that polynomial is called the characteristic polynomial of the matrix A, and is denoted as PA lambda, or simply P lambda, when there is no need to be clear about what matrix we are considering. Let lambda be an eigenvalue of A. So this is the same as saying that there exists, this notation means there exists a non-zero vector x such that Ax equals to lambda x. We are going to subtract both sides by lambda x. The x can be rewritten as I times x, where I is the identity matrix. Because of the left distribution property of matrix multiplication, you can rewrite this as A minus lambda I times x equals to 0. And so I'm going to write here something as short as there exists a non-zero vector x such that A minus lambda I times x equals to 0. This is the same as saying that the null space of the matrix A minus lambda I is more than the trivial space. But this is the same as saying that the nullity of the matrix A minus lambda I is greater than 0, because if you have a non-zero vector in the space, that means the dimension is at least 1. And then by the rank nullity theorem, the rank of a matrix is equal to the size of the square matrix, which is n minus the nullity of the square matrix. but then the nullity is greater than 0. That means the subtraction will result in some number that is less than n. Less than n means not equals to n. Then by theorem 3.9, a matrix is invertible if and only if its rank is exactly the number n. Now you have the rank is not the number n. That means the matrix is not invertible. And then from property number 7 in the determinant section, a matrix is invertible if and only if the determinant is not 0. Now the matrix is not invertible if and only if the determinant has to be 0, right? That's why being an eigenvalue for A means being the solution for this polynomial equation. After we solve the characteristic polynomial for all eigenvalues lambda, we can find all eigenvectors associated to each lambda by solving the following system of equation. Ax equals lambda x, which now we know that is equivalent to a minus lambda I times x equals to 0. And this is the same as you have the matrix A minus lambda I, and then the right hand side will be all zeros. Next, I'm going to do an example. So first of all, you have to find all eigenvalues. In order to find all eigenvalues, you have to solve the characteristic polynomial determinant of A minus lambda I equals to 0 for all eigenvalues. You will have to know what is A minus lambda I. So A minus lambda I. A is a 3 by 3 matrix minus lambda times I. A is 3 by 3, so the identity matrix here has got to be 3 by 3. Perform the scalar multiplication and the subtraction for matrices. You have A minus lambda I equals to 3 minus lambda 1 0, and then 0 1 minus lambda 0 4 2 1 minus lambda. And if you compute the determinant of A minus lambda I, it's going to be equal to 3 minus lambda times 1 minus lambda squared. Now if you really expand this one out, it is going to give you negative lambda cubed plus 5 lambda squared minus 7 lambda plus 3. And this is a polynomial that is called a characteristic polynomial. However, we are not going to do this in this example, because if you want to solve this equation equals to 0, it is much harder than solving this equation, the factor form equals to 0. So the determinant of A minus lambda I equals to 0 if and only if lambda is equals to 1, which I will denote as lambda 1, or lambda equals to 3, which I denote as lambda 2. Alright, so we did the first part here, find all eigenvalues. Next, we solve for the eigenvectors associated to each lambda values. That means you have to first consider lambda 1. In order to solve for the eigenvectors, you will need to solve the equation Ax equals to lambda 1 times x. But this is the same as solving the equation A minus lambda 1 times the identity matrix times x equals to 0. And it is the same as solving the system of linear equation written in the augmented matrix form, right? Where you have A minus lambda 1 times I on the left and zeros on the right. What is this guy? Well, let's go back several lines above. A minus lambda I is going to be 3 minus lambda 1 0 0 1 minus lambda 0 4 2 1 minus lambda. So if lambda is replaced by lambda 1, that's going to be 3 minus lambda 1 1 minus lambda 1 here, and 1 minus lambda 1 here. But lambda 1 is 1 in value. So this is going to be 2 here, 0 here, and 0 here. All right, and so this equation is equivalent with 2, 0, and 0 for the diagonal, 0, 0, 0 for the right hand side. What are the other values? So 1, 0, 0. Right, 1, 0, 0, 0, 4, and 2. So we are going to make changes on row 3, make it become row 3 minus 2 row 1. So this means that x1 is pivot variable. And the 2 here, x2 and x3, non-pivot. We can let the non-pivot variable to be free and then compute the pivot ones accordingly. Right. So this means that the solution set of a minus lambda 1I times x equals to 0. This is also known as the lambda 1 eigenspace of the matrix A. So this space or this solution set is x of the form x1, x2, and x3, where we know that x2 and x3 are non-pivot. So, right, so x2 and x3 is free. But then x1, you have to compute it using this equation. This equation means that 2x1 plus x2 plus 0x3 is equal to 0. And so it implies that x1 is negative 1/2 x2. So this is negative 1/2 x2. Now, in order to find a basis for the solution set, or in other words, the lambda 1 eigenspace, so this is going to be the same as negative 1/2 x2, x2, and 0, and then 0, 0, and x3. So this is equal to x2 times this vector and x3 times 0, 0, 1. All right, so it turns out that every solution or every vectors in the eigenspace corresponding to lambda 1 is in fact just the combination of the two spanning vectors here. And so this implies that the lambda 1 eigenspace of A is equals to the span of negative 1/2, 1, 0, and 0, 0, 1. Well, if you call this one capital X1 and this one capital X2, then you can easily see that x1 and x2 are linearly independent. Well, that means they form a basis for the lambda 1 eigenspace. All right, we have finished finding a basis for the lambda 1 eigenspace, but we haven't done so for the second eigenvalue we have, lambda 2, which is 3. So we got to do that. We are going to substitute 3 here, and we are going to get 0 here, negative 2 here, and negative 2 here. All right, we know for sure now that solving for all the eigenvectors associated to this lambda 2 equals 3 is the same as solving for the equation a minus lambda 2 times I times x equals to 0. And this homogeneous equation is the same as you write the augmented matrix. On the left, you have a minus lambda 2 times I, and on the right, it's going to be the vector 0. And this is equivalent with, by switching row 1 and row 3, so row 2 switch with row 3, we end up having, so row 3 become row 3 plus 2 row 2. At that time, you get, right, so this means that x1, x2 pivot. The non-pivot is x3. The solution set for ax equals lambda 2 times x, also known as the lambda 2 eigenspace of A is the collection of all x, 3 entries, x1, x2, and x3, where we know that x3 can be said to be free because that's non-pivot. x2 has to be 0. Well, this equation means that for x1 plus 2 times x2, which is 0, minus 2x3 is 0, and it implies that x1 is equals to 1/2 x3. So we can write 1/2 x3 here. Well, it turns out that all solutions of ax equals lambda 2x can be rewritten as x3 times 1/2, 0, and 1. And so in other words, all eigenvectors in the lambda 2 eigenspace is just a scalar multiplication with the spanning vectors. This implies that the lambda 2 eigenspace of A is just the span of this column vector. If you call this one x3, then it is independent by itself. And so you get the spanning, you get the independence. So this implies that x3 is a basis for lambda 2 eigenspace of A. And being reminded that lambda 2 is the value 3, right? And now let's consider example number 2. Using the result in example number 1 to compute A to the power 100 times x, where x is the column vector 2, 2, 8. We first express x as a linear combination of x1, x2, and x3. So we want to write x as A times x1 plus B times x2 plus C times x3. But x we know is 2, 2, 8. What is x1? What is x2? And what is x3? Right, we can go back to the previous example and we will see that x3 is 1/2, 0, 1. Remember that, right? Note that down. x1 is negative 1/2, 1, 0, and x2 is 0, 0, 1. All right, so we go down and fill in the blank. Negative 1/2, 1, 0, 0, 0, 1, and 1/2, 0, 1. From this equation, you can easily find A, B, and C. You should be able to find A being 2, B being 2, and C being 6. And so this means that x is going to be 2 times x1 plus 2 times x2 plus 6 times x3. Now if you apply A 100 times x, it's the same as you multiply the matrix A 100 with 2 times x1 plus 2 times x2 plus 6 times x3. Now remember, A is a 3 by 3 matrix. If you multiply A with A, that results in A squared is also a 3 by 3 matrix. And no matter how many times you multiply A with itself, you will always get a 3 by 3 matrix. So this is just a matrix. You multiply a matrix with the sum of vectors, just like you perform the linear transformation on the sum of vectors. You can utilize the linearity property of the matrix multiplication. And so that is the same as 2 times A 100 times x1 plus 2 times A 100 times x2 plus 6 times A 100 times x3. Now if you apply A on x1, then you're gonna get lambda 1 x1. If you apply A 2 times, that means A times A of x1. So this is gonna be A times lambda 1 x1. And by the scalar property, you can pull lambda 1 out and you multiply A with x1 first. But then A multiplied with x1 is just another lambda 1 for you. And so you have a square x1 equals lambda 1 square x1. You can easily see that if you apply that for 100 times, what you are going to get is lambda 1 to the power 100 times x1. And similarly, x2 is the eigenvector associated to lambda 1. So if you apply a 100 on x2, you are going to get lambda 1, 100 x2. Because x3 is the eigenvector associated to lambda 2. So if you apply a 100 on x3, you're going to get lambda 2 to the power 100 times x3. Substitute this into this equation. We're going to get 2 times lambda 1 to the power 100 times x1, 2 times lambda 1, because x2 is the eigenvector associated to lambda 1, right? To the power 100 times x2, and then 6 times x3 is the eigenvector associated to the eigenvalue lambda 2. So this is going to be lambda 2 to the power 100 times x3. 2 times 1 to the power 100. Now we can replace the x1 as the vector negative 1/2, 1, 0. And then plus 2 times 1 to the power 100 times 0, 0, 1. And then 6 times 3, which is lambda 2 to the power 100 times 1/2, 0, 1. If you combine all the vectors here, you're going to get this. All right, but still we haven't answered one of the questions from example number 2. Can we do the same for all x in R3? The answer is yes, because we found 3 independent vectors, x1, x2, and x3. And so every vectors in R3 would be able to express as a linear combination of the 3. Now the key is that the number of independent vectors is the same as the dimension of the space. Whenever you find a set of independent vectors that have the number of vectors being the same of the dimension of the space containing it, it becomes the spanning set and hence the basis for the space as well. This implies that for any x in R3, we'll be able to express x as a times x1 plus b times x2 plus c times x3 for some solvable a, b, and c. And so if we want to do the same thing, we apply a power 100, then we are going to get this. This is the reason why every vector x, we can apply the same trick. Let's consider another example. Example number 3. Find all eigenvalues and a basis for each corresponding eigenspace of the matrix B here. B minus lambda I is going to be, and then you compute the determinant of B minus lambda I using one of the tricks that I showed you. But if you pay attention, then you see that this is an upper triangular matrix. So the determinant can be computed by just multiplying the entries on the main diagonal. And if you solve for the eigenvalues, then you are going to get either lambda being 3 or lambda being 5. And so this is going to be denoted as lambda 1 and lambda 2 for the number 5 for simplicity purpose. Then we are going to find the lambda 1 eigenspace. In order to solve for the lambda 1 eigenspace, we have to do bx equals to lambda 1 times x. We know that this is the same as solving for the system of linear equation b minus lambda 1 times I times x equals to 0. And so you know that on the left hand side, the matrix of coefficients will be b minus lambda 1 times I. What is lambda 1? Again, remember lambda 1 is 3. So you substitute 3 here, 3 here, and 3 here. So the matrix of coefficients for this equation is going to be 0, 1, 1, 0, 0, 1, 0, 0, 2. And on the right hand side, that's going to be 0. So row 3 becomes row 3 minus 2 row 2. So we know that x2 and x3 are pivot variables. And that means that x1 is going to be non-pivot. All right, whatever non-pivot we can let to be free, and we have to compute the pivot. This implies that x3 has to be 0. The first equation implies that x2 plus x3 has to be 0, and so x2 has to be 0 as well. And so all the eigenvectors would look like an x of 3 entries, x1, x2, and x3. Remember, x1 is non-pivot, so we can let it be free. All right, we know that this is a free one, so we are not going to touch it. The other pivot ones will have to be 0. And so every vectors in this lambda 1 eigenspace, the solution set of this equation is going to be expressed as x1 times the vector 1, 0, 0. This implies that lambda 1 eigenspace is in fact just the span of that only one vector 1, 0, and 0. If we call this one vector x1, then we also know that x1 is a basis for lambda 1 eigenspace. All right, so next we are going to find lambda 2 eigenspace. Remember, lambda 2 is 5. So we need to solve the system of equation bx equals lambda 2 times x. So you will have negative 2, 1, 1, 0, negative 2, 1, 0, 0, and 0. And on the right hand side, you get all 0. Now, you even don't have to do anything because this is in echelon form already. So this is pivot, right? And we know that x1 and x2 will be pivot variable. And x3 is non-pivot. So this implies that negative 2x2 plus x3 is 0. In other words, you would have x2 equals 1/2 x3. The first equation gives you negative 2x1 plus x2 plus x3 equals to 0. And with x2 has been found to be 1/2 of x3, then this implies that negative 2x1 plus 1/2 of x3 plus x3 is 0. And simple computation will give you x1 equals 3 over 4 x3. You know immediately that every vector in the lambda 2 eigenspace is going to be of the form. That means every vector in the lambda 2 eigenspace is just a scalar multiple of the vector 3 over 4, 1 over 2, and 1. In other words, this implies that the lambda 2 eigenspace is equals to the span of that only one vector. If you call that one vector x2, capital X2, then you even know a basis for lambda 2 eigenspace. So this matrix B produces two lambda values and hence giving two different eigenspaces. Each eigenspace is a one-dimensional space. So you have two independent vectors, x1 and x2. So we go to example number 4. Using the result from example number 3 to compute B100 of x, where x is 1, 2, 4. As we have seen in example number 2, if we want to compute B100 of x, then the best way is to utilize the eigenvalues and eigenvectors of B. So this is going to be equals to, we'll have to express this as A times x1, B x2. We only have x1 and x2, we don't have another x, right? Those are the only two that we can find. We don't have x3 here, in this case, like in example number 1 and 2. First one was 1, 0, 0. And the second one was known to be 3/4, 1/2, and 1. If you solve for A and B, then you are gonna get A being negative 2 and B being 4. So this means that B 100 times x is going to be equals to B 100 times negative 2x1, 4x2. we know that this is going to be the same as multiplying b100 directly with x1 and b100 directly with x2, and then multiply the corresponding scalar, and then add the result because of linearity property. X1 is the eigenvector associated to the eigenvalue lambda 1, so there will be lambda 1 coming out every time you apply b on x1. And because you apply b on x1 100 times, you have 100. And then similarly, because x2 is associated to lambda 2, so lambda 2 will come out, and because you apply b 100 times, you are going to get lambda 2 to the power 100. All right, so this is negative 2 times, what is lambda 1? That was known to be 3. So you have 3 to the power 100 plus 4 times lambda 2 is 5, so 5 to the power 100 times x2. And you can also go ahead and replace x1 and x2 by the corresponding column vector 1, 0, 0, and 3 over 4, 1/2, and 1. Right? As the result, you should be able to get negative 2 times 3, 100, plus 3 times 5, 100, and then 2 times 5, 100, and then 4 times 5, 100. Now the question is, can we do the same for all x in R3? We immediately realize that this can be a trouble. It is unlike in example number 2, because in example number 2, we were able to find enough 3 independent vectors so they can span the whole R3. Now we only have 2 vectors. How can we span a 3-dimensional vector space? That's impossible. Right? So since it is impossible to span R3 3-dimensional by only 2 independent vectors, x1 and x2, the answer is no, because there would be some vector x that you will never be able to express as a linear combination of x1 and x2. For instance, if you consider the following vector, that is 1, 1, 1, if you want to write it as a times x1 plus b times x2, that means you want to find a and b such that a times this vector plus b times this vector equals 1, 1, 1. And so this is equivalent with solving a system of linear equation. A plus 3 over 4b equals 1, 1/2 times b equals 1, and then 1 times b equals 1. Immediately from the last 2 equations, you get b will have to be 2 and b 1 at the same time, right? So this is impossible. So from example number 2 and example number 4, we realize that, well, there is a major difference between A and B. A is good, right? B is not as good. Definition 5.2. An n by n matrix is said to be deficient if it fails to provide enough n independent eigenvectors. So from this definition, we immediately see that because A produces enough n independent eigenvectors, A is a good one. A is not deficient. But B, 3 by 3 matrix B, fails to provide enough 3 independent eigenvectors. B only produces 2 independent eigenvectors. And so it is deficient.